Is there are
My dad, yeah, my one of my teenagers does. My dad.
Hey, all. How y'all doing?
Doing pretty well, and you?
Oh, I'm wearing my Minnesota shirt and sitting in the was it Sweet Springs Nature Reserve in Los Osos. So I guess things are going really well. Let's think. Maybe I want to share a screen to make an announcement, and then we'll just start there and move forward. As always, just interrupt me if you want, and because I sometimes don't see what's going on in the chat. If you got a question, just unmute and talk. If I don't respond to the chat quickly enough. Okay. So one thing I want to note is, again, we got this exam coming up. It does feel as though it's really quick compared to that first one. But, if you think about it, each week of class is like 2 weeks in a regular term. And so, yeah, it's like our midterms were at the end of week 4 and the end of week 6. It doesn't feel so awkward anymore. I will say though that the key reason is the material changes considerably right after chapter 5. And in particular, the material in chapter 6 and later relies super heavily on the last couple sections of the content in chapter 5. And so it's a really good idea to have an exam right at the end of chapter 5 that covers, chapter 4, etc. But the key is that way you'll all have read up and studied and learned to the best of your ability the content of sampling distributions, what we're going to talk about in class today and the topic of the lab today. You'll have a good understanding of that, which will, as we drift into early next week, will allow you to sort of grab onto more easily the material in chapter 6 and later chunks of the course. Okay, so it's structured very carefully for that reason. I've tried in past classes where we'll sort of have the next exam like after chapter 6, and students have an understanding of the chapter 5 and 6 content, less so as demonstrated by how well they do on the final exam than if we have the second exam right after chapter 5. So awkward timing from the point of view of the 5-week version, but it is what it is, and it's for a reason. Okay. So one thing I want to mention is that to get you ready for the exam, what you could do is look at the second sample exam, and maybe I'll do that right now just to talk about the length of our exam versus this second sample exam. I'm looking here, and this is something across these 5 questions. This would be about an hour worth of questions. So if you can do this second sample exam in about 60 minutes, you're working at about the right pace to do our exam, which you'll start on possibly tomorrow. You'll do just fine at that. So there's the sample exam. Some people like to quickly check versus sort of like a brief set of numeric answers because I'll give you some details, but not much. So, for example, you can't do it. Sample size is too small, or 0.7037. These are the sort of answers that would be viewed as correct. But yeah, your worked out full answers might be better for the sake of prepping. The brief answers are probably good if you're just trying it out and you want to just quickly check your work. But then if you want to know why did I get that right or why did I get that wrong, the full answers are a little bit more content. Many students say they do prefer the brief answers as well as the full answers. So you get both. There you go. No problem. Okay. Okay, so that's one thing. Second thing I want to mention is if I look into what we're covering today, it is content which is on the exam that starts tomorrow. Okay. And so if you were looking at these homework problems out of 5.4, 5.5, and 5.6, while indeed they are due this coming Monday by midnight, I would certainly spend time and get them completed by tomorrow class time when you could ask about these exact questions during class. Tomorrow class time would probably be best spent with content on that will be on the exam, and so ask about it, or content from the sample exam, and that's great. We could move into chapter 6 a little bit if we don't have a full 40-50 minutes worth of questions. I suspect that you'll have questions, and the questions will be really worth spending time on before we move further forward. Okay, so that's my plan is for tomorrow, Q&A related to stuff that will be on your test. The test, again, live as of about 1 p.m. tomorrow, and you have to have it finished by Friday at midnight. Now, that's local time zone. Some of you are not local right now, but, figure it out. It works. Okay. Any questions about administrative matters?
Labs and like the exam coming in, because right now I only have the first two homeworks.
Can you okay, wait. Can you repeat your question from the beginning? I don't think I heard the first part.
When are all the labs and the exam, like at latest, going to be inputted?
I think you should have your exam score already. I could be wrong about that, but I set it up so that way you should be able to re-enter the assignment and see what your score was on that. If I didn't set that up correctly, I need to make a change. But I know some students have already talked to me and said, well, hold on, how come I got partial credit on problem 4? So I have the feeling that they've been able to see their answer. So I'd say go back into the assignment, and inside the assignment, I put my solutions. Okay. So the solutions I use for assigning grades, a complete set of correct answers are there. So you should be able to find that there, as well as all of the homeworks that are passed, as in through homework, I guess 2B, you should be able to sort of click your way into the assignment and see answers for each of the homework assigned problems. And so I should look to see if where the grader's at in terms of grading. And if you're referring to that, it could be that the grader simply hasn't done it yet. And that may tie to the labs as well. Labs tend to be a situation where you get full credit if you did it, because it's basically our way of saying, okay, this class is half asynchronous. That is the asynchronous chunk of class. Being here for the quote lecture and then Q&A type stuff, that's on you. You do it when you want, if you want to, and that's good. You could watch the video later if that's better for you, or you could watch it twice, live and then later. But the asynchronous lab content is something where if you turn it in, you get full credit. And if that hasn't been done yet, it could be that the grader just hasn't been doing it, and I'll just go ahead and do that later. But I pretty rarely see anyone with less than about 95% of the points on the lab activity. And I always make sure at the very end that I look to see if every student, not every student, I look at every lab group and verify that indeed they have credit for the assignment. And so if there's someone who's missing something late in the term, I usually go and look and see if I could find what might have happened. But basically think you should have full credit if you've been working on the assignment and someone clicked submit. And I've even had an email as of, I think it was yesterday. Someone said, oh yeah, we neglected to turn in our lab in week 1. We did it, but we didn't hit the submit button, and it's all good. It's just a matter of getting it done and turning that in. So Tarzan, does that answer your question?
Yeah, thank you.
Cool. Any other administrative questions? How about content related questions from the homework problems assigned yesterday, or concepts that came up in class yesterday? Or heck, you want to just have another example of something that happened yesterday in terms of probability. Working through a probability question start to finish. I can do another one if you want. I'd like to think I'm patient and willing to wait. Now I feel like I'm stalling, and none of you have asked for an additional question. So, hey, screw it. I'm going to do it anyway. So I want to show you another problem and a way that you could use some of the probability rules that we talked about yesterday to tackle something that came up in consulting with a student who about a decade ago sort of came to me working on his senior project. And he was in sort of like a what they call the supply chain management major, or I don't even know what it's called. But he was working with this person sort of in this weird sort of intersection of engineering and business. And it was a situation where we have these RFID tags, and then you build them into a box. Okay, so you think Amazon might sponsor research like that. That's cool. They take that little seam along the box, where you have the cardboard overlapping the other cardboard in this one little stretch, and you glue it there. They just slap an RFID tag right inside of that box. And so you're sort of thinking three-dimensional box. Oh my gosh, that is supposed to be straight. So here's my three-dimensional box, and here's the seam along that edge. And we're just going to put the RFID tag sort of like right there. Okay. And as this, yeah, I'll grab onto that in a second. Thanks for the query. So as these boxes boxes don't flow. As the boxes travel along your conveyor belt, at Amazon, they're heading sort of that direction. And you want to know, has it hit a particular location? And the whole thing's supposed to be automated. But one of the parts of the automation is this one little tunnel that it has to go through. And I attempted to draw that three-dimensional. I'm sorry if you are fussy at me about three-dimensional drawings. You have a collection of 5 RFID scanners along this arch that the boxes travel through. And they're all supposed to be able to spot whether this box has gone through, because each RFID tag has a unique identifier on it. Some of you probably know more about that than I do. All I know is it's got like a name, okay? As it travels through here, the box might very well be oriented differently than what would be, quote, optimal or ideal. The person who packs the thing might lay it down sideways, okay? Maybe indeed this little RFID tag could be on the very bottom in the corner, on the underneath portion. But as it's going through this little arch, you want to know if it's going to be scanned. Do we spot the thing? Okay. And you know what? You're gonna miss some of them. Okay. But you got another arch down the way a little bit. Okay, further down the conveyor belt, and yet another arch even further down. And so the question that this individual had is, what is the chance of spotting an individual RFID tag? And we oriented it towards the geometry, like literally if the box is laying flat with the tag underneath versus all the different positions that the box could be in, would this collection of these 5 scanners be able to spot it? And so at each point in time, you either spot or you miss the box. Okay, so most of the time we spot it. The probability that in any one of these arches we spot it is 0.90, because that's a convenient number to work with. Okay, and if there are 5 such arches, so what's the probability that we spot the box at least one time across 5 arches? So 5 of these arches, or scanners, if you will. What's the probability that we spot it across the 5? And we suggested yesterday something like the following. We asked the question, well, if this is a hard problem to solve, if I rephrased it as the opposite, would it be easier? So my question, what's the chance that I spot it at least once across the 5 arches? Well, the opposite, logical opposite of spotting it at least once is missing it every single time. So the probability that we spot it at least once, the number of spots, is greater than or equal to 1. is 1 minus the probability that the number of spots is 0. Okay. And what's the chance that we miss it? Well, that's easy to sort of figure out. The chance that we spot it is 90%. The chance that I don't spot it is then going to be 10% or 0.1. And we have to now make an assumption. And the assumption is if I spot it on the first arch, my ability to spot it in the second arch is not impacted. So it's sort of like, okay, the box went through the first arch, I spotted it. That doesn't change the chance that the second arch will spot it or not. Alternatively, or another way to say the same thing is the chance that it's missed, like I missed on the first arch. That doesn't impact the chance of missing it on any of the later arches. The chance that you spot it in any one location is not impacted by whether you spotted it earlier or later. So we have a collection of independent arches, okay? That's like the probability, if you will, the probability that the second arch is a spot is equal to the probability that the, second is a spot given that the first is a spot, okay? If you spot it on the first one, it doesn't impact the chance that you spot it on the second. Okay, so how would I know with that independence, how would I now be able to calculate the overall chance of spotting it at least once across the 5 separate arches? And the answer is going to be, again, through that 1 minus rule. The chance that I spot it at least once is 1 minus the chance that I miss it 5 times in a row. And missing it 5 times in a row will be the chance that I miss to the power 5. Okay, so this is 1 minus, well, 1 minus the probability that I spot it, 0.90 to the 5th. And so that's 0.1 to the 5th power, 1 minus 0.1 to the 5th power. I'm thinking I'm going to end up with 0.99999. So you've got a 99.999% chance across 5 arches of spotting this box as it goes through. Okay. Notice I use the 1 minus rule here, and I used the concept of independence to tackle the problem. If we don't have independence, it won't work. Some of you might have cleverly spotted that this is also sort of binomial because you got an n of 5 and you've got a chance of spotting it of 90% or a chance of missing it of 10%. And so this is, the number of spots being 0 is the number of misses being 5. Okay. And so you could use the binomial distribution directly for this one. Okay. Any questions about this example? Okay. So question 5.1, problem 2. So let's see if I can find that section. Okay. Well, that's the wrong class even, so that won't even be the right book. So let's try the right book. In chapter 5, problem 1, part 2, or section 5.1, problem 2. So let's do a drag over here and let's see if we can find it. Maybe I'll clear that whole thing. So 5.1, problem 2, let's talk on that one for a little bit. Okay, so if, and problem 2 starts way over here, if an engineering firm is constructing power plants at 3 locations, E1, E2, and E3 correspond to you've completed by the contract date for each of the 3 plants. Draw a Venn diagram that depicts these events as intersecting circles and then show each of the following. So I don't know that I'll get all of these, okay? But certainly E1, E2, and E3 are the 3 separate events we're talking about. So our sample space here you've got E1, E2, and E3. And so at least one of the power contracts or power plants is completed on time. I'm thinking that's just going to be this whole shaded area across all three groups. So yeah, at least one of them is completed on time. I could write that as E1, union E2, union E3. Maybe I should switch from yellow because indeed yellow is hard to read. So let's go with maybe pick a different color. Let's go with a darker green. Okay, so all of the plants are completed by the construction date. That's part B. Part B, that's sort of shown in green here. Oh, all three of them are completed in time. E1 and E2 and E3. Okay. So if I were to now, let's go ahead and erase that and talk about part C. Let's actually maybe skip C. Only the planet site 1 is completed by the date. Let's talk about part D. Only planet site 1 is completed by the date. That means you are in E1, but you cannot be in E2 or E3. So part D looks sort of like that. Okay. Part F, I'm going to jump to that one real quick. And F here, either the plant at site 1 or 2, or both of the two plants, either of 1 or 2, or both of the two plants are completed by the construction date. Either the plant at site 1 or site 2, or both. So site 1, but not site 2. Site 2, but not site 1, or both site 1 and site 2 are completed by the construction date. And I should include those as well, because part F does not refer to plant 3 at all. Okay, so I think, Muska, that is tackling your question. You want to do a follow-up on that? Okay. Okay, so F still a little bit confused on. Well, F refers to only sites 1 and 2, yeah? And it says either site 1 or site 2 or both. I would probably write it as either site 1 or site 2. Okay. I would just say E1 union E2. That's all I would say, which tackles the question, what about E3? Well, this doesn't refer to E3 at all. And so if I've got E1 and E2 only, I would go ahead and shade both of those in. Now, if E3 is over here, I'm going to say, well, let's even say we added that into the figure afterwards. Okay. So indeed, E1 or E2 or both E1 and E2, we've shaded that here with our top figure. The E3, you could just add that in afterwards because it's not part of this problem at all. It's just that it's part of the drawing. So it's not part of F in any way, shape, or form, but it's in the figure you set up to start. Okay. Okay, so I think cool. So let's maybe move into something new. And in chapter 5, section 4, it's all about random variables. Okay, so I'm going to abbreviate random variable RV, and RV, a random variable, okay, is a process for generating an uncertain numeric outcome. As an example here, if I have a, well, okay, so let's just maybe do a figure first. Okay, so here's our sample space for an experiment, okay? And each of the possible things that could happen inside the sample space end up creating a number, okay? So anytime you have a mapping from the sample space to a collection of numbers, okay, you've got a random variable. The random variable is itself the process, okay? It is the mapping that takes any item in the sample space into the number. So I'd like to try an example of that. Here's the example. Oh, hold on. Here is the example. Okay. And how to, okay, come on. Darn it. There we go. Maybe I could now do it. Shoot, I have to stop the share and restart because I did something silly. Okay, now start again. Okay, so here is an example. I'm going to roll a die 3 times. Okay, so roll die 3 times. I'm going to say X. Okay, the random variable X is the result of the first die roll. Okay, and y'all know that, yeah, literally on a die roll, you could get a 1 or a 2 or perhaps a 3. I'm going to go all the way up to a 6. Okay, but yeah, literally X is just then that number. So the die roll result, okay, the die roll is going to be one of those 6 numbers or 6 possible sides being face up. And then there's the die roll, and there's your X, and the X is 1, 2, 3, 4, 5, or a 6. Okay. Y could be the result of a second die roll. So let's go with first die could be a red die, first, well, let's just say it's a red, and Y could be the blue die result. And Z could be the green die result. Okay, so X and Y and Z are all random variables. Yeah, they're all a process for generating an uncertain numeric outcome. And shoot, X could be a 1, or it could be a 3, or it could be a 5. You sort of know something about the possible values X could take. Heck, from the classical approach to probability, you'd say the chance of any particular value for X is exactly 1 in 6. Okay. And so I guess I could list off the possible values X and then their probabilities. Okay. So the possible values 1, 2, 3, 4, 5, or 6. Chance 1 in 6 all the way through 1 in 6. So it's something that you are familiar with already. We already talk about probability distributions. A random variable is defined by a probability distribution. Okay, so it could be something simple like just rolling a die. It could be even more complex. W could be the minimum of X and Y. Yeah, literally, I could take 2 dice, roll the pair of dice, 1 red, 1 blue, and find the smaller of the 2 numbers. Okay, and W being the smaller of the 2 numbers, again, it's an uncertain outcome, but it is numeric. Okay, so W is a random variable. Let's even go with Z being the average of X, Y, and I'm sorry, we already have a Z. Let's go with we'll go with V. D being the average of X, Y, and Z. So X plus Y plus Z over 3. Or heck, a variable U, a random variable U could be literally the standard deviation of X, Y, and Z. Okay, so I could create all 3 numbers, X, Y, and Z, by rolling a die. You know, I got 3 dice. I'm going to roll all 3 dice. I've got a list of 3 numbers. I could calculate the standard deviation of those 3 numbers. And from the standard deviation of those 3 numbers, that's going to be an uncertain value, and it's certainly numeric. If I do it again, I'll get probably a different X, probably a different Y, and probably a different Z. And my standard deviation will also probably be different. The standard deviation at the smallest, I guess it could be, would be 0, because if all three numbers are the same, I would have a standard deviation of 0. But the standard deviation could be as large as maybe even 3 in size. Like if I get a well, not exactly 3. If I have a 1 and a 6 and a 3, okay, my standard deviation would be almost 3 in size. Okay, so there's a variety of possible U's, there's a variety of possible V's, there's a variety of possible W's. We have a lot of random variables that you could create with just dice. Okay, so one of the random variables we sort of care the most about, for the sake of our understanding moving forward in chapter 5, section 5, is the average. Okay, so let's talk about a sort of conceptual box model. Okay, so there's a population. And I'm going to draw the population as, maybe I'll show you the histogram. And there's some sort of number out there, the mean of the population that I'm sampling from, a standard deviation sigma of the population that we're sampling from. And you're going to sample at random via a simple random sample n individuals. And by simple random sample, what we really mean is every possible sample of size lowercase n from the population is equally likely to every other possible sample. Okay. Some people ask about with replacement versus without replacement. I'm going to say without replacement is the way I'm thinking about it right now. But if the population is big, so big that the chance that you would get the same number again is really next to impossible, we don't really fuss about with or without replacement. I'm just going to say you're going to get a collection of numbers, x1, x2, all the way up through xn. And those n values are going to give you a sample mean, x bar. You could even calculate a sample standard deviation, s. So what here is random? What is a random variable? Well, the first thing that I draw out of the box, it's random. Unknown, but it's certainly going to be a number because we're sampling from a numeric distribution. That's random. The first value, random. How about the second value or the nth value? They're all random variables. And because each of them is a random variable, the average itself is also going to be random. If you're sampling from a population, the sample average will be unpredictable. In some ways, you could tell me how likely it is to be in this range or that, and we're going to learn that in chapter 5, sections 5 and 6. But certainly there is randomness in the sample mean. Heck, the sample standard deviation, also a random variable. So the real question that I have is, tell me about the distribution of the possible X bars. Tell me about the distribution of what could indeed happen. What could happen if I'm sampling from a population? I guess it's possible if I'm sampling 5 individuals from the population, I could get the 5 lowest. Possible that I could get the 5 highest. It's possible that I could get 5 that are all really close to the average. We don't know what's going to happen, but we do have information about the list of what could happen in the population itself. Now, typically you don't know the population, but I will tell you as a fact, the typical value of, or the expected value of the sample average, you might write that as mu of x bar, the mean of the possible sample means, is just mu. And I just love saying this sentence, the mean of the mean is the mean. That is funny, okay? The mean over all possible samples of the possible sample means is the mean of the population you're sampling from. That's a fact. Another fact, second fact, the variance of the possible sample means is sigma squared over n, or if you want to write it this way, the standard deviation of the possible sample means is just sigma over the square root of n. Okay. There's a third fact out there that we'll discover in the next example, but I want to hold off on that fact for just a little bit. Let's sort of get into our simulation. And I think in the Canvas for class today, one of the things I suggested or had, oh, darn it. Okay, well, I'm going to take a screenshot of that so I still have it, and then I'm going to clear it. And then we could rewrite those equations in a bit if you ask me to do so. Okay. I provided for you a link in the Wednesday, Thursday section of this week to an applet, and that's two of my colleagues came up with this a while back. It says 2021, but they came up with this one dating back into the early 2000s, and this is the 2021 version that I'm providing you a link to. But in this link, it looks right there. I've got data on a variety of different possible populations I'm sampling from. The data set I'd like to use is called pennies. You could choose like the Gettysburg address if you'd like, but I'm going to go with the pennies data because it's easy to explain. And let's resize this so we can see more easily. We've got data on in the year 2000. They asked a group of students to bring in all the pennies they could find where they lived. Okay, so each student in class wandered in with a handful of pennies across the whole year, and they're trying to identify the age of these pennies. Okay, and so you know from the year on the penny, and if you haven't noticed yet, just look at the penny you have, or any coin from the U.S., and it has like a year on it, the year it was minted or created. So in the year 1999, I think, we have a penny from 1989 is 10 years old, so this is collected in 1999. The 1984 penny was 15 years old. We've got data here on the age of these pennies. Okay, so this data distribution looks very skewed to the right, and one of the pennies is pretty old. It's like 50-something years old, okay? So I've got the entire population here, and I'm showing you the population just like downstairs, okay? So here's the population I'm going to sample from. Now I want to sample from that population because we're talking about sampling. And let's take a sample of size, say 1. And that's a silly thing to do, but let's sample from the population. And we might have gotten one penny that's from 76, which in 99 would have been 23 years ago. And I'm going to just make note of here's what I've seen so far. And then I'm going to plop it over there. Okay, so let's draw another sample of size 1. This time it's a 13-year-old penny. I'm going to put my 13-year-old penny right here. And I'm adding a 13 to my histogram. Over here, we're developing a histogram of the values that I could see. And rather than doing this 1 or 2 at a time, I'm going to go for another 8 all at once. Okay. And you can see the next 8 sampled pennies. They're all right here. Okay. And we see an average across the 8. Okay. So let's try maybe one. Let's better yet, a sample size 1. And let's try 100 samples all at once because that will save some time. I'm going to draw 100 separate samples. The last of the 100 was a penny 658 in the data set, 1986, 13 years old. I'm showing it here. And here's the value that we're spotting. If we were to draw another 100 and another 100 and another 100 and another 100 and another, I'm drawing lots of hundreds all at a time. I could sample many times. Like I've now got like 3,500. Oh, let's go for 4,000. Let's go for 5,000 separate samples from my population. Okay. And if I'm sampling exactly one item from the population, it looks as though my list of the possible samples that I could see is a lot like the list from my original data set. My histogram of what could happen is a lot like the histogram of the population I'm sampling from. Okay, so that's if I have a sample of size 1. I'm going to reset that. What if my sample is of size, say, 2? If I sample 2 individual pennies, and I'm going to just sort of grab a whole 100 of them all at once, the last sample of size 2, one of the pennies was from 97, one from 99, ages like 2 and 0. On average, they were 1 year old. I'm going to plop the average of the sample of size 2 over here. And if I continue to, let's go for a full-on 5,000 separate samples of size 2. Well, it's 3,000. My gosh. It doesn't take too long to do, but here's 5,000 separate samples of size 2. And I'm spotting something. I'm spotting that on average, across my samples of size 2, I've got 5,000 of them. The average of my 5,000 samples of size 2 is like 12.4, 12.3. For my population, the average was 12.3. Not surprising that the samples in that way are looking like the population you're sampling from. And the standard deviation of my sample means here, my sample means like a draw of 2 will give me my sample of size 2. And I'm going to find the average of those 2. And then I'm going to create that histogram of the 5,000 separate averages of size 2. The standard deviation of that is like, oh my gosh, 6.8. A little bit less than the standard deviation of the population I'm sampling from. If I were to, instead of a sample of size 2, what if I were to go for a sample of size 10? Okay. I'm going to grab a sample of size 10 now. Actually, I grabbed a whole 100 of them. In the last sample of size 10, I got a couple that are quite low and one that's sort of on the larger size here with 30 years of age. Here's the average 9.2 years, and I've shown it here, and I've got now 100 separate samples of size 10. So down in the lower right corner, we're developing a set of sample averages for my collection of samples. And like before, there's 1,000 separate samples. Let's go for 5,000 because I like 5,000 because I've done it so far a couple times today. Okay, so really close to 5,000, so slow down and stop. Okay, so my last sample of 10 right here, shown to you. Here's the histogram of the last sampled values. You can even see them shown relative to the population I'm sampling from. And in this case, I don't have any that are really unusually large in my sample. Okay, and my sample average is like 11.8. It's still pretty darn close to the population average of 12.3. In fact, my average across my 5,000 separate samples, my average of my sample averages is like 12.3, like the population I'm sampling from. But my standard deviation, the distribution of how far the sample average is away from the population mean, that's now a lot smaller than the standard deviation of the population they're sampling from. Okay, let's try one more case because we tried 1 and 2 and 10. Let's go ahead and try like 30. Okay, so I'll reset that. And now my sample of 30, we're seeing in the histogram of the population I'm sampling from, I'm seeing quite a few that are small, some that are large, just like my population that I'm sampling from has some large values. I see them in my sample. I see quite a distribution in my sampled values. This is my last of the 100. And I'm going to take that sample average and plop it over here along with the earlier 99. So far I've got 100 and we want 5,000. So let's do another 900 all at once. Boom. Now we're at 1,000. And I'm sorry, I'm going to start that one over. A sample size of 30. Okay, click. And we want 1,000. Better yet, I'll go with 5,000 separate samples of size 30. Reset and go. Okay, so here's your histogram of the 5,000 separate samples, each of size 30. And what we're spotting is still it's centered where the population is centered, but the spread now is lower. It's almost as though there's more precision now that you have a larger sample. Larger sample gets you more precision. The sample average goes closer to the population average. The sample average is likely to be close to the population average if your sample is large in size. But I'm also spotting something really sort of interesting, and it's eventually the shape of the sample averages follows a normal curve really very well. Okay, so that's that next rule that I wanted to tell you about. Okay, and then we're going to sort of get into a problem that that is sort of set up nicely by this context. So third rule. Sometimes that the distribution of the X bars is normal in shape. Okay. If the population is normal, that will work. If you're sampling from a normal population, the distribution of the sample averages will follow a normal curve. Okay. Or if n is big enough. And by big enough, I'm going to say, because someone always says, hey, is n big enough? I'm going to say it depends on the context of the situation, depends on the shape of the population distribution. If the population distribution is horribly skewed and bimodal, big enough, n is a little bit larger than if you have a distribution that's not horribly skewed and with two or more modes. Most distributions are big enough, I would say n is at least, say, 25 or 30. Okay. So basically, if you see a sample of n being 25, you say, oh, I can do that. If you're sampling 25 times in a fair way from a population that would show up in this class's problems, you should be fine. If in real life, however, your population, again, has horrible skewness and n of 25 might not be large enough, but that's for a different class. Okay, so let's take advantage of this setup and see if we can get further into our understanding of how to tackle these problems. Okay. So A, if the population is with mu equal to, and let's go heights of adult male Californians, 70 inches is the average, 5'10" is the average. Okay. And standard deviation of adult male heights is 2.5 inches. If you have a sample of size n equal to, and I'm going to go with 25 because the math works out brilliantly here. If you have, actually, let's go, instead of 25, let's go with an n of 4. Okay, so that's a smallish sample size, or from a normal population. Okay, and the heights of adult male Californians follows the normal curve pretty darn well. Okay, the probability distribution of the sample average height has mu of the X bars being 70 inches tall, and the standard deviation of the possible X bar values would be sigma over the root of n, in this case 2.5 over the root of 4, and this is 1.25. Okay, so you could show me that normal curve of possible sample means. So here are the possible X bars. Okay, on average, you should be about 70 inches. And if you go up and down about twice the standard deviation, that should capture, with the empirical rule, about 95% of the values. So 72.5 and 67.5. Okay, so let's rephrase that a little bit. If you grab 4 random adult male Californians and say, how tall are you? And average the four heights. You'd be a little surprised if the average is more than 6'1.5". 6 foot tall, 72 inches. The average of four people being above there seems rare, or below 5'7.5", also sort of rare. And you could even tell me the exact chance of 71 inches or smaller, because cap phi of 71 minus 70 over 1.25 is something we can calculate. So we're home free. So in a problem like this, you're home free as long as you have a normal population. There is, and I hopefully you'll be able to bear with me for another few seconds, and I'm going to talk about what if you don't know that the population is normal in shape. Okay, we can still solve the problem as long as we know the sample size is n large. So let's change that 25 or 4 to a 25. Okay, so if we have a sample of 25 individuals and we don't know that the population is normal, but we do know that the population mean is 70 and the standard deviation is 2.5. The probability of the distribution of the possible x bars, the possible sample average, is still centered at the same spot. Even though the sample is larger in size, it doesn't change where it's likely to be averaging. But our sigma of x bar, the standard deviation of the possible sample means, is now a 2.5 over the root of n, which is now 25. So this is going to be a 2.5 over 5, 0.5. So the resulting distribution of the possible sample means centered again at 70, but the spread is now a lot less than before. If I go up and down 2 standard deviations, I'm going to have a plus or minus 1. Shoot, 71 and 69 inches. So 71. You'd be very surprised to see the average of 25 randomly chosen adult male Californians being taller than 5'11". It would be really surprising. And we can find that out even if you don't know normality. The reason is our sample is large enough in size. Okay, so that's a good place to stop because I've gone over and you now know everything you need to know about sampling distributions for the sample mean. In this section of the material, the homework is really, really helpful. And I hope that we have a lot of good questions tomorrow about the homework. So that way you are on the right page before we move forward into the exam. Okay, so I'm going to stop the recording in a little bit, but you're totally free to go. If there are any questions, I'd love to answer them. However, before I stop the recording, any quick questions before you go off and do the lab on sampling distributions? Okay, I'm going to stop the recording now, and we will